Hello, my name is Yesenia Beltran, and I am part of the New Mexico Tech Physics Department. Today, I will be discussing the topic of dark matter. The idea of dark matter was first discovered by a Swiss physicist named Fritz Zwicky in the 1930s. When studying the velocities of individual galaxies, he first proposed that mass was missing as the velocity of the known mass was not the same as the calculated velocity. It wasn't until the 1970s that the other scientists encountered the same problem. Scientists expected that the farther away the gas cloud surrounding a spiral galaxy was from the center, the slower it would be moving, just as more distant a planet is from the sun, it orbits slower. A research paper conducted by Ben Moore discusses that for many galaxies, the farther out from the center you went, the faster the clouds are moving. Using the Doppler shift, scientists were able to find the radial velocity of the spiral galaxies. From there, they used the radial velocity to find the gravity to yield the mass of the spiral galaxy. Finally, comparing the calculated visible mass to the mass found by velocity. There was a huge discrepancy that could only be explained by dark matter. Today, I will argue that discovering the nature of dark matter is necessary to understand the history and the future of the universe. I will go through the evidence of dark matter, forms of dark matter that can be detected, and the nature of dark matter. We can find more evidence for dark matter in the images of clusters of galaxies. In the research paper, uh, Dark Matter by Bikram Phukunam and Bitnam Nath, they found that images of galaxies at large distances compared to those of clusters and which appear as background objects behind clusters of galaxies are often seen to be distorted. This effect can be described as gravitational lensing. The amount of distortion measures the distribution of mass by Einstein's relativity theory. You can you can use this to calculate the total mass of the clusters that coincides with the mass calculated from the velocities. To understand the gravitational lensing, we must first look at Einstein's theory of relativity. This theory proposes that the universe exists within a flexible fabric of space-time, and the objects with mass bend space-time, which defines gravity. Gravity cannot only affect the path of objects, but the path of light as well. This can be seen in the effect of gravitational lensing as light gets distorted due to large masses that have more gravity. Gravitational lensing was used to detect dark matter for many years, although more recently, scientists have been using gravitational microlensing. Microlensing is the changing brightness of a distant object due to the interference of a nearby object. Using this technique, scientists were able to find that dark matter cannot be strongly concentrated or exist in the form of regular matter objects, thus giving us very little to work with. A research paper called A New Era in the Search for Dark Matter in the Universe, conducted by Gianfranco Berton and Tim M.P. Tate, discusses attempting to detect dark matter by using dark matter self interactions. They believe the trace of dark matter self interactions could be found in the merging systems like merging galaxies. These traces could create energy or momentum exchanges that could produce some kind of wave. Scientists believe that the best way to describe the nature of dark matter is through weakly interacting massive particles, or WIMPs. WIMPs are massive particles that are electrically neutral and do not interact very strongly with other matter. With such little information about the nature of dark matter, it is believed that not only one WIMP can account for all of the dark matter. The most compelling WIMPs are neutrinos. Neutrinos are a subatomic particle that are similar to an electron but have no charge and a very small mass. These particles are abundant in the universe and interact very little with matter. They are incredibly difficult to detect, thus making them a perfect candidate for dark matter. In the research paper, A Dark Matter, a Primer, by Catherine Garrett and Duda Gintaras, it was found that neutrinos only account for part of dark matter because the neutrino dominated universe would have formed large structures first and then small ones, meaning clusters of galaxies would have formed before galaxies, and galaxies would have formed before stars, and so on, which we know isn't true due to the Big Bang Theory. To conclude, dark matter is nearly invisible as it cannot be seen, interacts with matter, and has mass. We know it exists due to the formation of galaxies, Einstein's relativity theory, and the Big Bang Theory. Effects like gravitational lensing and gravitational microlensing can help us detect dark matter. WIMPs, more specifically, neutrinos, can help describe the nature of dark matter, although they do not account for all of the dark matter. Although we have such little information on dark matter, it makes up the majority of our universe. Better understanding the nature of dark matter will help unlock the history and the future of our universe. Knowing how this abundant form of matter works can help us predict the future expansion of the universe and explain the current phenomenon. Thank you for your time.